Right, good morning. Any questions, any comments? So I want to show you some stuff about building on what we talked last time. More interesting stuff coming from spin-1/2 chain. So let's consider 1D like spin 1/2 and nearest neighbor Heisenberg chain. And last time from like Lieb-Schultz-Matisse theorem we saw that this model has gapless excitations. Or another way to say the same thing is like the ground state is not unique, or the excitation gap here is order j over n, and it goes to 0 as n goes to infinity. So we also saw that linear antiferromagnetic magnon also has 1 over n dispersion, because because E is proportional to K and K is proportional to 1n. But in the case of 1D chain, that's not the case. Not the case here. Because no long-range order in 1D antiferromagnet. Okay, so that's the summary of last few lectures. So how do we look at these things? We can look at correlation functions, and in this case of spin models, we can look at spin correlation function. So let me write what it looks like. So what we are interested in is like the ground state, and take any S I and Sj and calculate its expectation value in this ground state. And what you are going to find is this is going to be minus 1 over I minus j. So it's going to alternate between the distance, and this is going to be so-called power law. So this is like I minus j, but on top of this there's like some logarithmic correction. That's not very important, but in numerics you are going to see this. So this is I minus j. So this is small log correction. And this kind of power law, so when you have this kind of power law in the correlations, what does it mean? Does anybody? So when you have a system with power law correlations rather than exponential decaying correlations, that means like strong correlations, right? Power law correlation means like stronger than exponentially decaying. And if there is like a correlation at very large distances, what does it mean? From our knowledge of phases and phase transitions. So this is like a critical system, right? So this is quantum, because this is a quantum model, exactly like criticality between water and vapor and ice, something like that. We also have it, but this is like a quantum system. That's why it's called quantum critical. So that's why this system is actually very interesting for people studying mathematical physics, because they can test many of their theories, like conformal fit theory and critical exponent, all those things. And this means like any snapshot, if you look at the lattice, looks something like this: up, down, down, dot, dot, dot. So it's going to be very similar to the Neal order, which we actually ruled out. So it's like Neal order. But now I will show you that actually there is like a difference from the Neal order, right? So and the difference is going to come in the excitations about the ground state. Now let's consider, so excitations. So we have a degenerate ground state, and above this degenerate ground state we want to put excitations. Like we increase the energy, and these excitations tell us about the ground state. And these excitations, if you want elementary excitations above ground state, are called spinons. So these are spinons, like electron, phonon, or like photon. So this is spin-on. It's like a spin particle. It's just a name, and I'll tell you what this new particle is like. Let's think about this order, right? So there is like, let's consider this order 1. So there is like one type of ordering, like up, down, up, down, up, down, up, down, and so on. But this is right. This is not the only option. If I take every spin and flip it, it would be indistinguishable from energy point of view. So this order 2 is going to be like, to take the shortcut, let me just copy this piece and put it like this, and put down, up. Right? These two are they have the same energy. And now what I want to do is like, let me take order 1. So let's take order 1 and flip only one spin. And let's take it in the center. So I'll take this, and I'll bring it. I can also do it here. So I'll flip this one, for example. Now this is up, and you can see here I have 3 up spins, and I increased energy because this is like a model, like, so this is like J Si dot Sj, right? When 2 spins are positive, J is positive, you increase the energy. Now I increase the energy, that's why I call it excitation. And locally, if we also, okay, there is like some delta E, something like J, maybe 2J, this is non-zero. But also there is also a spin, right? Initially spin was here, right? This spin was down, and now it is up, and total change is 1. The magnitude, at least the change is 1. So this is local change in spin. But now what I can do is like, I can write, so I can, for example, hop this. I can take this guy and take it to here. Now there will be 2 up here, but it's not going to change the energy. So the energy between this configuration, let me show you, let me draw you and show it. So this one, and for example, okay, there are like 3 ups here. What I want to do is I want to change this one and this one. So energy is the same. Now you can see I gain from this bond, but now I have this bond. So I only gained 1 bond and gave 1 bond. So it's still degenerate. And I can do the same thing here. For example, this one can go to here and like that. Here. But as I do it, you can see somewhere in the lattice, there is no way, right? I have to have a point where 2 spins are up. Whereas here I had 3 spins are up. Right? The energy cost of this little, like 2 spin, is smaller than this, right? And total S is also 1/2 here, right? Whereas I was going to have like S is equal to 0, now I just flip half of a spin. So this is like locally delta S is 1/2. It's as if I fractionalized. What I can do was like delta S was equal to 1 in the like reasonable world. But here, if I only look at the here locally, I fractionalize that excitation. Okay, this is like fractional. That's what it is called, fractionalized excitations.
May I ask, do we call this delta S equals 1 as a local change? I mean, there is another 1/2 at the bottom left. Again,
here?
Yeah.
So here, if you look at this, down, so every time I have the same up, up, or down, down, this is like energy punishment, right? Here I have what? So this is down, up. This doesn't cost anything. This is up, up. This is a cost. This is up, up. This is another cost. Up, down, there is no cost. So if you want, I have 2 units to pay. But here, if I come here, it's like down, up, nothing to pay. Up, up, 1 unit of payment. Up, down, nothing to pay. And here similarly, up, up, there's like 1 unit of payment.
Again, 1/2, right?
Yes, 1/2 here, 1/2 there.
But we say globally we still have delta.
Exactly. In the entire system, I need to have at least 2. So these are called spinons, right? This excitation is called spinon. And they are exactly like particles, but these are like, you can see a different kind of particle. And I have to have 2 of them. I cannot have a single spinon because I created 1 and then I delocalized that. And so this one is, for example, also if we are called domain wall. And there's here another domain wall. And this domain wall is distinguishing what? It is distinguishing, if I call like this one order 1, right? This is up, down, up, down, up, down. So I have here order 1, right? So this is, so this region is 1 order. And every time I make a mistake, I jump to other order, right? Here I have a mistake, then so if this is order 1, this is going to be order 2. And it's as if I have like an up magnet and down magnet, and there's like a domain wall between 2 magnets. But this is quite different because this is fully quantum. And similarly, I have...
Right side, this is also...
Exactly. This is also like, let me, if this is order... Of course, order 1, order 2, I cannot distinguish. But if I call this order 1, this is order 2, and this is order 1 again, because I know the mistake, and this mistake should change whichever. If I have up order, if I have blue order, I need to change to red order. If I have red order, I need to change to blue order.
It's symmetrical. Like one and order 2, I think they should same. I know we cannot distinguish.
Yeah, we cannot distinguish these 2, but we can see the domain wall between these 2. Right? In a magnet too, right? In a magnet, if you look at it, right, there is like some up and down, but there is no like, there's like an arbitrary like orientation. You cannot distinguish those 2. But when you change from one to other, that's what you can distinguish. So, and this actually behavior. So this is what they call spinon and fractionalization and all those things are exactly similar to so-called Schrieffer, it's like Schrieffer-Heger, so-called SSH model. And this actually is a physics of so-called polyacetylene. There's like a one-dimensional polymer. It has very interesting like transport properties, and the physics here is exactly similar to there. And there we are fractionalizing charge. Here we are fractionalizing spin. If you want, you can look at physics, contents of physics 410, and you can also read Gervin-Young on that. Okay, so this is for the plain spin 1/2 Heisenberg chain. Now, what we can do is like we can modify the Hamiltonian and see how things change to understand what we are dealing with. So let's try to suppress this power law Néel order. It's not like long range order anymore, but there's still some power law Néel order, and we want to frustrate that. So we can, so this is also like a jargon. You can frustrate, that is by putting two competing ordering tendencies. And the way people do this is like, I have the Hamiltonian. So the first one is usual, but this is J I SI dot SI plus 1. So this is nearest neighbor coupling. So far that's the only thing we had. But on the top of this, I want to put some J prime with the second neighbor coupling. So this is SI dot SI, not plus 1 but plus 2. Good. Now, so we want to form, like, to have the antiferromagnets, we want to put up, down. But now this side and the third side, because of this, they also want to be up, down. But now this spin, is it going to align itself with this guy or this guy? Right? Is it going to be up, down with his neighbor, or is it going to be up, down with his next near neighbor? Right? That's what we call frustration. So each spin is frustrated by two competing tendencies. And this is also like a model that's, I think, very difficult to study for the general J prime. But if J prime is equal to J over 2, this model is exactly solvable. So let me show you how this comes about. So this is, if this is J over 2, what we are dealing with is, so this is J over 2, sum over I. I'll put 2 here, SI dot SI plus 1 plus SI dot, okay, I can try to put vectors, but it's taking too much. Something like this. And I want to write this in a little bit a different form. So because there is like a summation, I can do the following. I can take one of these, and I can say this is SI minus 1 dot SI plus SI plus 1. And I can do this SI minus 1, SI plus 1. Right? I didn't do anything, I just relabeled the lattice sides. And now let's look at this thing. So I want to consider, for example, this thing, SI minus 1 plus SI plus SI plus 1. So these are all spins. And I want to take square. So you can see here, okay, let me spell this out to convince you this is something we can calculate. So this is, there will be SI minus 1 squared plus SI minus 1 times SI plus SI minus 1 dot SI plus 1. So I take this times this times that, and I'll repeat it. So plus SI minus 1 plus SI squared plus SI dot SI plus 1. So I take the second terms, and plus SI plus 1 dot SI minus 1 plus Si plus 1 dot Si plus Si plus 1 squared. Now we know quantum mechanics. For any I, what is Si squared? Right? Exactly. This is h bar squared s plus 1, and this is a constant. Whether it is up spin or down spin has no effect. So then, so this thing, and this thing is going to give me a constant, and that constant I actually calculated. It is like, so these are, so these three are going to give, they are like n sides, and each is going to give s plus 1, and it's h bar square, and we are taking h bar 1 anyways, and I'll call this a constant. So what is remaining is Si minus 1 Si, so this is nearest neighbor, so this is 1. So this is next nearest neighbor, so this is nearest neighbor, this is second, so this is third, and this is nearest, and this is, there are like 4 nearest neighbors, and I need, you can see 2 here, whereas I have 1, 2 next nearest neighbors, and I need 1 here. So I can say then, so this Hamiltonian is equal to this one, so this is sum over I, Si minus 1 plus Si plus Si plus 1 squared. You can see I have 4, whereas I need 2, so I'm going to put here j over 4, and this additional, I don't care about what it is, I'll just write constant for this. Okay, we have exactly the same Hamiltonian written in a different way. Now I want to minimize that. This is a Hamiltonian, if you want, this is like an energy, and I want to minimize this, and I am like adding 3 spins, right? We also know addition of angular momentum. Spin is angular momentum. So what we can do is, okay, S1 plus S, let's consider S1, S2, S3. Any 3 spin is fine. So it can be 1 or 0, right? It's like either triplet or singlet. And S3 can be either 1/2 or 1/2. Now I need to add 1 and 1/2. Then S1 plus S2 plus S3 is going to be either, okay, 1 minus 1/2 is 1/2 or 3/2, and this is going to be 1/2. So in total, S1 plus S2 plus S3 is going to be either 1/2 or 3/2. And if I want to minimize the energy, which one should I choose for here? Is it 1/2 or 3/2? 1/2, right? I need to choose the minimum one. So this is going to be ground state. And once I do that, I have the ground state. And how does it look like? So if you take 3 spins, so the picture is something like this. 2 neighbors, choose 2 neighbors, this one or this one, they have to be singlet, and the third spin has to be free. So if these 2 are singlet, I put them in like a circle, and this one is going to be free spin. Or I can do the following. I can raise this, and I can put the singlet here, and okay. So this is spin 1, 2, 3. This is 1, 2, 3. I have 2 options. I either have like singlet between 1 and 2, or singlet between 2 and 3. So this is called, in the literature, is valence bond. So I think when people first recognized things like this, I think they thought they were like similar to like something they saw in chemistry, but now I think we just use it, and it has nothing to do with chemistry. Now, then, okay, by the way, this J over 2 model it has a name. This is called Majumdar-Ghosh model. But the name of this model at exactly J prime is equal to J over 2 is Majumdar-Ghosh model. And there are many models, right? Because we have like a many-body problem, it is unsolvable, and anything we can solve helps us understand the physics. And that's why people just come up with models. They're like Heisenberg model, Hubbard model, Majumdar-Ghosh model. I'll show that there are like AKLT model, there'll be Kitaev models. I don't think we'll have time for that. But every time you study these models, you understand something new, and it shows you things beyond the model. And you have to study the model. If you want, you have to do numerics, you need to do proofs, but you need to know the limits of the model as well. And the ground state of this thing is like this. So I have these sides. If you want, let me just duplicate. And I have two options. And exactly like above, I can do one or the other. And the option is like I can like dimerize, like put singlets like here. And this is a ground state. Or I can put the singlets like this. Right? And the ground state energy is like, okay, so I have this additional constant. Here I have, this is S squared, and total S is 1/2. Then this is going to be, this is what? This is H bar squared S plus 1, and S is 1/2 here. Then this is going to be H bar squared 1/2 3 over 2, right? And the ground state then is E is equal to 3 over, is it 16, right? Is it 16 J H bar squared plus this constant. Something like this. And the ground state is twofold degenerate. So this one and this one. So this is, if you want, order 1. This is not exactly order, but so this is ground state is twofold degenerate. And sometimes, because this is like kind of like a crystallization, people call this valence bond solids. And it breaks translational symmetry, if you want. So translational symmetry is broken because of this solid order. That's why it's called solid. So this is broken translations. And you can see like Lieb-Schultz-Matisse theorem is satisfied, but it is satisfied in a very different way. So in this case, there are like two ground states, right? It's another way of saying that ground state is not unique, or another way of saying this, there are like excitation is gapless. But still, we can consider these things and what is the excitation above these two degenerate ground states. And now that's what I want to consider. So let's consider elementary excitations. And what I can do is, for example, let me just take this one. Right, these are all singlets. And I can break one bond at some point, and breaking one bond at some point is like putting a side here, which is not singlet, right? This doesn't do any singlet with its right neighbor or left neighbor. As a result, this bond is going to cost energy. So this is, so if you want, any triplet was spin 1/2, but this triplet is 3 over 2, right? And as a result, this delta E is going to be, there's like J over 4 times 3 over 2 h bar, and additional energy you need to pay is, I think, something like 3 over 8 J and h bar. Let's take 1. And what is the spin? There's also the spin cost, and spin cost, initially spin was 0 everywhere. Now I have just 1/2 spin, so delta S is also 1/2. This is also fractionalized. Why I call fractionalization? Because the simplest thing I can do in a lattice is I take this up spin and turn it to down, and this is delta S is equal to 1. Or I can take down spin to up, and this is also delta S is equal to 1. But here you can see that I created something which is half spin. That's why I call it fractionalized. And this also from the previous picture. So here, another way to look at this is also a domain wall. And this domain wall now distinguishes order 1 and order 2. There are like two choices. And these two degenerate ground states, if you want, they're like one magnetization, another magnetization. And there's a domain wall between these two. And this is also exactly like SSH model. So I want to show you one more model, and I want to connect it to a little bit of high energy physics, and then I'll finish it there. So let me first draw the phase diagram of this Majumdar-Gash model, MJ phase diagram. So we are interested in the phase diagram as a function of J prime over J, and here there's like something 0, like there's no nearest neighbor, next nearest neighbor coupling, so this is like nearest neighbor Heisenberg. Somewhere over here there is like 1/2, so this is Majumdar-Gash MG model, and this is exactly solvable. And we believe, okay, let me take it to here. There is actually an extended region, and of course this has to be verified numerically. So this is spontaneously dimerized phase with these fractionalized excitations and all those nice things. And this piece is so-called quantum critical that I outlined in the beginning. So this is quantum critical. And there must be somewhere here a critical point, J prime C over J, which should be determined numerically. I don't know any analytical results for that. Now, let me show you one more model, how these things play out, and then I will finish it there. So let's also consider, so as you can see, dimerization comes out in the ground state, even though the Hamiltonian itself is not dimerized. The Hamiltonian is translational invariant, but the ground state breaks the translation symmetry. Now let's break the translational symmetry in the Hamiltonian by manually, like consider dimerized spin model. Spin 1/2. So dimer is like these things, right? These are dimers. You take pairs of sides, you dimerize. That's the right. Yeah. If you have like 3 sides, I think it's you can also polymerize. But they call each of these things is called dimer. And when you have like a state like this, you call it dimerized. Yeah, language is the biggest barrier, unfortunately, to learn these things, because the people invent their own language, and if you are a newcomer, you don't understand. And in the Hamiltonian, I want to consider, let me just draw the Hamiltonian rather than writing it. So these are sides, and so on. And I want to do two kind of bonds. Like there's like these solid bonds, and so on. Let me call these J1, 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 and let me alternate between these dashed bonds, and this one is J2, J2, and J2. So now translation symmetry is broken in the Hamiltonian level, right? I break it by choice. Now Lieb-Schultz-Matisse theorem does not apply, because there we had to use translation symmetry of Hamiltonian. The question is, what is the ground state of this model? And how is it related to these other models? And is there like some way to go around and then still find Lieb-Schultz-Matisse theorem and with gapless states? We'll see. So for this, let's do the simplest thing. Let's consider first J2 is equal to 0, right? Then there is nothing to talk about. All dimers are decoupled, right? These guys, they don't know anything about each other. And you have a dimer here, a dimer here, one dimer here, one dimer here. And each one has to be singlet, because that's what the energy minimization requires. And in this case, no ground state degeneracy. Why? Because I cannot take this bond and put it here, because here there is J2 is equal to 0. There is no energy. Actually, doing this is going to cost energy, because this guy is now going to be in the triplet, and it's going to cost energy, so you cannot do this. So the dimer, the singlet, has to be here, here, and here. And they have to be uncoupled from next dimer. And the excited state is highly degenerate. So this is the ground state without degeneracy, and excited states are massively degenerate. Because I can break this bond, it is going to cost an energy. I can break this bond or this bond. In total, I have order of n excited states, because I have n different sites to break the bond, maybe n over 2. So this is like converting. I can convert, I don't know, this one from S is equal to 0 to S is equal to 1 triplet by breaking this bond. And this is exactly like magnon. What was magnon? I had like this ferromagnetic site, right? Ferromagnetic order, and I was going and replacing one of them. But because of translational symmetry, this downspin was delocalized, and that's what we called magnon. In that case, I'm breaking this from S0 to S1, and this is going to be delocalized, because breaking here or here or here, there is no energy cost. And if you want, the system is going to prefer some kind of Bloch wave formed from these different options. And this thing, okay, let me try to put this in the center. Look, let me copy this. I have one more thing to say about that. And let me, for example, break this bond. What does this mean? So breaking this bond means I have like a triplet, like up and up, something like that. And this is S is equal to 1. Whereas this one is S equal to 0, this is S is equal to 0, and so on. And because of this, right, this is also gapped. So this is gapped excitation. Now we can think about the phase diagram as a function of energy gap. Right? So let's think about this energy gap, and let's try to draw. So this is I want to look at gap as a function of J2 over J1. So this is energy gap delta. So this is 0. So I know certain points. So this point, let's say this is J2 over J1, 1. This is the usual nearest neighbor Heisenberg model where Lieb-Schultz-Matisse theorem applies, and there's like gapless excitations. Therefore, I need to have 0 gap here. But as soon as I go away from this, there'll be some gap opening. And here, J2 over J1, 0, I just calculated, right? It has to have some gap here. Let's call it like this. Something like that. So these are, I just interpolated the 2 points I know exactly. But as J2 over J1 goes to negative values, what is going to happen is like this is going to turn into some kind of spin-1 model, right? Because these spins, they are going to combine and they are going to form something like spin-1 system. And that spin-1 system we are going to study later. It's so-called, okay, it's always gapped. And this gap here is called Haldane gap. Okay. And you may ask, is it possible to have like spinons on this model? Let's try to put spinons on this model. Suppose I take this guy and I try to delocalize these, right? So, okay, I need to also remind you, these solid bonds are J1, like these empty bonds are J2, which is smaller. So if I try to do this, like erase this one, take one of these spins here, and put something like this. Now it looks as if I actually have delocalized the spinons, right? Exactly like I did before. But so what is the difference between this and earlier model? Can you see? Can I do this without any energy cost? I mean, it may be hard to see at first, but this actually costs energy, right? So this is J1 bond, which is strong. So this is J2 bond, which is almost 0, right? In the limit of J2 is equal to 0. So there is no energy benefit of putting a singlet here. Now you have a triplet here and you increase the energy. So now if you try to propagate this fractionalized spinon, like try to propagate one more time. So you are somewhere here. Now maybe two of these. Let me draw it like this. So you put it here. Then you need to have another spinon here, right? So this is solid, empty, solid, empty. So this is going to be solid, and the singlet is going to be here. Now you have a second cost. Every time you miss your singlet in the strong bond, it's going to give you additional energy cost, right? So this is one unit of energy, this is second unit of energy, and as these spinons are getting away from each other, you are going to pay more and more in energy. So energy increase as spinons move away from each other, in this model, each other. And like now, my question is like, do you know any other system where you pull two things and this force increases, right? What's that? Like in any physics, in quantum theory, any area of physics, in which area we have two things, you pull them from each other. The longer you pull them, the stronger they attract each other. But what's that? Strong force, right? What are the particles? Quarks, right? This is exactly like quarks. We are saying that quarks are confined, right? Because if you take two quarks and pull them apart, they pull each other stronger and stronger and stronger. That's why you cannot do it. So quarks are confined. Similarly, here in this model, spinons are confined. Because as you separate them, they pull each other stronger. So they want to be together, and when they are together, there is no spinon. They are. That's the meaning of confined. Whereas in Majumdar-Gash model and in some other models, if we have spinons without energy cost, we call they are deconfined. Okay. So now, okay, that's all I wanted to show you today. Next time I will try to focus on Spin-1 and see what differences we can obtain in like Spin-1 chain and playing with all of these, and what exactly solvable models we can have in Spin-1 chain. Any questions? All right, thank you.